A single stray signal, barely a few millivolts strong, can turn a billion-dollar spacecraft into a silent ghost drifting through the void. The culprit isn't a meteor or a software bug, it's an invisible war being waged on its own circuit boards. This is the critical world of electromagnetic compatibility, or EMC, in mixed signal spacecraft design. Let's break down how we keep our missions safe. First, what is a mixed signal system? It's where the delicate world of analog sensors meets the noisy, high-speed universe of digital processors. Analog circuits listen for faint whispers from the cosmos, temperature, light, radiation. They require pristine, quiet conditions to work correctly. Digital circuits, on the other hand, are constantly shouting, switching on and off millions of times per second, creating a storm of electrical noise. The core EMC challenge is preventing the digital noise from deafening the sensitive analog ears. This unwanted transfer of energy is called electromagnetic interference, or EMI. On a PCB, this happens through crosstalk, where signals on adjacent traces couple, and through the power and ground planes that all components share. So, how do we enforce peace? The first and most fundamental rule is proper grounding. It's the foundation of all good EMC design. We use solid ground planes, unbroken sheets of copper, to provide a low-impedance path for return currents, essentially absorbing noise before it can radiate. Imagine a messy room versus a clean one. Daisy-chaining grounds is like leaving wires everywhere, creating antennas. A ground plane is like a perfectly clean floor. The second principle is partitioning. We create dedicated neighborhoods on the circuit board, one for analog, one for digital, and one for power systems. This physical separation minimizes the chance for high-frequency digital noise to couple into sensitive analog traces. We keep the noisy neighbors away. We even partition the ground plane itself, sometimes creating a moat or a split, forcing return currents to stay within their respective zones. Our bridge between these worlds is often a single component, like an analog to digital converter, placed carefully straddling the boundary. Third, we use filtering and decoupling. Think of these as tiny, localized shock absorbers and noise traps placed all over the board. Decoupling capacitors are placed right next to a chip's power pin. They act like mini reservoirs, supplying the instant current the chip needs for switching. This prevents the chip from pulling noisy current spikes from the main power supply, which would pollute the power shared by all other components. We also use ferrite beads and inductors on power lines. These components act like bouncers at a club, blocking high-frequency noise from passing through. The final defensive layer is shielding. This is the brute force method, enclosing sensitive circuits or noisy components in a metal box, a Faraday cage. This shield intercepts incoming electromagnetic radiation and shunts it safely to ground, protecting the delicate circuitry inside. It also works in reverse, trapping the noise generated by a component and preventing it from escaping. For spacecraft, these principles are pushed to the extreme. The vacuum of space means we can't rely on air for insulation and must manage heat carefully. More importantly, spacecraft are constantly bombarded by cosmic radiation, which can flip bits in memory or induce transient signals that mimic EMI. A robust EMC design helps mitigate the effects of these radiation-induced events, ensuring the system can recover gracefully from an upset. Every gram of mass is critical on a spacecraft, so we can't just add heavy shielding everywhere. Designs must be incredibly efficient and precise. Before launch, these systems undergo brutal testing. They're placed in anechoic chambers and blasted with electromagnetic energy to find any weaknesses. Engineers use near-field probes to sniff out noise hotspots on a board, pinpointing the exact trace or component causing a problem. And sophisticated software simulates the electromagnetic fields across the entire design long before the first piece of hardware is ever built. In the unforgiving environment of space, good EMC design isn't just an engineering detail, it's the invisible shield that ensures a mission's success.